The process of integration using the fundamental theorem of calculus involves generating an antiderivative function. Now often though, or sometimes I should say, the antiderivative function is not itself an elementary function. We usually start with an elementary function and we hope that the antiderivative function will be an elementary function that we can deal with in making the calculations that are necessary for integration. But that is simply not always the case. For example, here, if we're trying to deal with this, if f of x is something as simple as the square root of 1 plus x cubed, then what are we going to do with this? How do we integrate this over any particular interval that we'd like? And I'm talking about definite integration here, and so we're kind of looking for the area under a curve. And if we're having to perform that task, then and someone asked me, how would you do that? I'd say, grab the calculator. It's very easy with the calculator, you know. So I think what we're doing here in this section is optional. This is kind of an antique now that we have calculators at our disposal. Certainly we would not use a manipulative technique to deal with this situation in real life. In business or in industry, we just pick up the calculator and bam, 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 we have the integral. But as a historical note, let's take a look at what had to be done 20 years ago before graphing calculators came on the scene and so forth. And it's rather interesting to me philosophically that here we have a topic. The first topic is the trapezoid rule, and we're also going to talk about something called Simpson's rule. But these two techniques are now obsolete, and they're made obsolete by virtue of the graphing calculator. And it's interesting to me, philosophically, that the people, the mathematicians, that long ago developed this process in a fashion contributed to the development of the device that makes the process obsolete. Kind of interesting, isn't it? It kind of brings into focus the idea that we, all of us, indeed stand on the shoulders of our ancestors, and those that follow us will stand on our shoulders, and it's just the nature of life. At any rate, let's talk about the technique. Now, we can't go through the antiderivative idea. We have to maybe resort to our fundamental idea of integration, the idea of the limit of a sum of rectangles, that is, the limit of a sum of some areas. Well, let's think about that over a particular interval. Now, if we're going to make this calculation by hand, then we're going to limit the number of rectangles that we have available. Now, that presents an interesting problem, because when we had an infinite number of rectangles, that is, as n approached, it's the limit as n approaches infinity, you see, and so the number of rectangles is approaching infinity, so they're getting infinitely narrow, you see, as n approaches big, big, big numbers, those rectangles become very, very narrow. And that's why it didn't make any difference whether we chose the left bottom side, you see, or the right bottom, the right side of the bottom of those rectangles to take f of in order to get the height or the length of those rectangles. You see in the calculation, we could have chosen any point along that ith interval to take f of in order to get the height. Doesn't make any difference. But if we limit the number of rectangles, we limit the number of subintervals that we divide our overall interval into, then we've got a problem. Because no matter how we configure this rectangle, rectangles simply don't work very well. If this is, now consider this to be a magnification of the of one of the subintervals. So we would have an interval that maybe stretches across the entire board, and then we have that subdivided into many subintervals, and this is just one of them. Okay, so we have a subinterval, and we want the area of the subinterval to be added to the other areas along the way. Okay, if we choose to inscribe the rectangle, then we're leaving out all of this area under the curve. So this is going to present us with an inaccurate value. If we use the circumscribed rectangle, then we're adding too much area here. This area is not under the curve. Even if we take the midpoint gives a better approximation, but even if we use the midpoint of our rectangle, we still get some area that we get some value over here that we don't want. We don't have some up here. This is a pretty good approximation, it looks like. But maybe we can come up with some kind of structure, some kind of figure to use in this process that will give a very accurate approximation, even if we choose to use very few sub-intervals and therefore very few figures for the calculation. Here's what I'm talking about. Suppose we decide to use a trapezoid, and the trapezoid is configured this way. We take f of x sub I minus 1, f of x sub I, and we make a trapezoid out of the situation. Now the trapezoid would look something like this. I'm just barely going outside of that curve at this point. And if all of the figures are trapezoids, then it sort of doesn't matter how this graph goes. We're going to get a pretty good approximation of the situation. Now, think about the calculation of this area for this trapezoid. You see, remember that the area of a trapezoid is, well, there's usually we look at the parallel sides up and down. So it would kind of be like this. If we usually look at it, we configure trapezoids a lot of times like this, and the parallel sides are up and down to one another. Well, here they're kind of across one another, so we have to take that into consideration. But when it's like this is kind of familiar, so I'll use this as a model just for the time being, but we end up taking the average of the upper base and lower base. So we add these two lengths, and then we divide by 2 and multiply then times this height. Okay, so it's the average of the upper and lower base times height. Well, the upper and lower bases are these two sides, all right? And to average those two, we would add f of x sub I minus 1 and f of x sub I and divide by 2. And then the height is simply this distance right here. It's x sub I minus x sub I minus 1. All right, so the area then is f of x sub I minus 1 plus f of x sub I all over 2. This is the average of those two sides. And then we would multiply by the length of the interval. Now, to generalize the situation, the length of the interval is going to be figured early in the problem as b minus a over n. It's the same as x sub I minus x sub I minus 1. Now, I'm not going to show you, you can look at the algebra involved in the development of the trapezoid rule in your textbook, and I invite you to do that. But I'm just going to show you the results of it. This is more of a historical note than anything else, as we mentioned before, and quite an optional kind of event, I'm thinking. But the trapezoid rule says that the integral from a to b of f of x dx is approximately b minus a over 2n. Now, the 2n business, if you slide this 2 over here, it kind of gives validity to the idea of the b minus a over 2n. All right, and then the f of, we're multiplying times the f of x naught plus 2 times f of x sub 1 plus 2 times f of x sub 2. And I'll tell you why these 2's occur here in just a minute. We'll understand why that's happening in this mathematical form. And then we add all the way to 2 times f of x sub n minus 1 plus f of x subscript n. Now, in this configuration, the x naught is the beginning of the interval and the x sub n is the end of the overall interval. A is equal to x naught, and x naught is less than x sub 1, and x sub 1 is less than x sub 2, and so on all the way down the line. And then when we get to x subscript n, that is the value b. Okay, so let's see how the trapezoid rule works. It's remarkably accurate even using a small number of trapezoids. And again, just realize that this was the method of choice. This was one of the methods of choice before calculators came along, that we had to figure out an integral within an interval involving a function that we couldn't really integrate. And so we had to calculate that area somehow, and here's how it was calculated. Let's consider this function that we talked about earlier, this square root of 1 plus x cubed over the interval 0 to 2. Now look at it graphically. The graph of this looks like this over this interval from 0 to 2. And we're going to use 4 trapezoids here. Only 4 trapezoids, and we're going to approximate the integral here within that interval, this definite integral. And we'll see how remarkably accurate the process is. Now we're going to divide using 4 trapezoids. So I'm thinking, okay, if I divide it here in half, and then I divide the half in half, and go to the end here and divide that in half, you see, then we have these 4 trapezoids. And let me just tell you, before I go on into the calculations, this first trapezoid, that first trapezoid involves f of x naught plus f of x1. This is the x1, that would be x2, x3, x4. Okay, this is f of x1 would be this distance. And that distance is used in the calculation of the area of the first trapezoid. But f of x1 is also used in the calculation of the area of the second trapezoid. And that's why all of these intermediary x's have a 2. When you look at 2f of x1 plus 2f of x of 2 plus 2f of x of 3 and so on. That's why, is because all of those edges of the trapezoids are used twice in the overall calculation. Okay, algebraically, now we can easily see the value of x sub 1, x sub 2, and so on by looking at a graph like this. We're dividing 1 in half, and that's a half, and that's 1, and that's 1 1/2, and that's 2. Now algebraically, we could make the calculation like this. If n is 4, then the length of each interval, I guess we could call it the length of each, it's actually the height of each of those trapezoids is b minus a over n. So it's 2 minus 0 over 4, or 1/2. So we can calculate the x subscript numbers like this. X naught is the beginning of the interval 0, and then x sub 1, just add a half, and then for x sub 2, add another half, and then for x sub 3, add another half, and now we're at x sub 4, and that's 2. So that gives us our values that we're going to plug into the relationship. So this integral, this definite integral, is approximated by b minus a over 2n times this. All right, here's what we had before. And notice that we're only going up to x subscript 4. So it's 2 minus 0 over 2 times 4. That becomes 1/4. All right, now f of 0 plus 2 times f of 1/2 plus 2 times f of 1. You see, these are just those little x subscripted things that we calculated just a little bit ago. All right, those little x values. And then we would, to evaluate this, f of 0, we're going to just pop 0 in place of x and evaluate. This becomes 1. And then f of 1/2 means 1/2 cubed plus 1. Take the square root of that, and we get this. And I have approximated each one of those along the way. And adding these, we would find the integral, the definite integral, to be approximately 3.28. Now, I need to tell you that the actual integral is equal to 3.24. And if we had used, now notice that we get a pretty good approximation just using 4 trapezoids by letting n be 4. If n were equal to 8, then we would get a value of 3.25. Wow, extremely accurate by using only 8 trapezoids. A second technique that we're going to talk about right now is called Simpson's rule. And the basis of Simpson's rule is a figure that's not trapezoidal, but the top of the figure instead of connecting endpoints of a subinterval, which is what the trapezoid rule kind of does, it actually makes a curve between those two. Here's how it works. Suppose we have, let's just call this x0 here, and x1 and x2. Now, notice that with the trapezoid rule, we would be forming a trapezoid within this interval. Well, here we're extending the idea to 3 of these x's, let's say. And here's what we do. We find f of x0. We find f of x1, let's say it's right here, f of x2 right here. And in finding the area, we're going to find the area not just here, but we're going to find the area here. And that area is going to be found by using as the upper bound here a curve containing these 3 points. Now, in algebra, you actually calculated the equation, the quadratic equation, given the coordinates of 3 points. And that's kind of the basis of the algebra for this, that you can actually come up with the equation of a quadratic that contains these 3 points. And therefore it'll be curved. You see, it'll be a curve containing the 3 points. Now that curve will not perhaps be exactly the same curve that we have here on our original function, but it'll be extremely close. And then that is the basis of Simpson's rule. Now, when you go to the next grouping here, all it takes is to add 2 more points, you see, and then you start, this becomes the left side point, and then there's a point sort of in the middle, and then a point on the other side. So here we are at x sub 2, and then we go to x sub 4 for the next grouping here, and therefore at the end of this whole process there would be an even number for this subscripted value at the other endpoint of the overall interval. Okay, so n would be even in this circumstance. Simpson's rule looks like this. I'm going to leave the algebra of the whole matter for you to look at in the textbook. You may have interest in how Simpson's rule is developed, and then again you may not. I think what's fascinating is how accurate it is. The integral from a to b of f of x dx is approximated by b minus a over 3n times f of x naught. Looks a lot like the trapezoid rule, doesn't it, up to here, except we didn't have the 3 here, but f of x naught plus 4 x sub 1 plus 2 x sub 2 plus 4 x sub 3, and so on. And in the middle steps here, it's 4, 2, 4, 2, 4, 2, 4, 2 as coefficients until you get down to the end, and it's 4 f of x sub n minus 1 plus f of x sub n. And the x sub n would be the right bound of the interval. Okay, let's use Simpson's rule to approximate the integral that we looked at earlier using the trapezoid rule, and we'll use n to be the same value that it was before. Now, we were talking about n being 4 before, and there were 4 trapezoids that were used. Now here we're going to use an n of 4, but there are only going to be 2 groups of 3. You see, if you look at the graph of it, let me sketch it over here now, and you'll see what I'm talking about. And it was something like this. Here's 1 and 2, let's say, and the graph looked something like this. And so when we divide into 4, we're actually sort of partitioning like this, and we're using these 3 points as a group and these 3 points as a group, you see, in the configuration for Simpson's rule. Now, this doesn't, we don't see this isn't evident when we look at the formula for the rule, but that's really what's going on here. There are only 2 regions that are being evaluated here, but the evaluation process is occurring with a lot of calculations that look like this. Okay, anyway, it's b minus a over 3n times f of x naught plus 4 times x sub 1 plus 2 times 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus f of x4, and that's all there is to this particular problem because n is 4. Oh, I underlined the dx here in the description of what we're doing because I forgot to write dx in the last problem. Please forgive me for that, and I wonder if you caught it, but it is a mistake not to write the dx after the function here. It's f of x dx when we're integrating. At any rate, let's go through the calculation. It's b minus a over 3 times n. So it's 2 minus 0, and n is 4, so it's 3 times 4. And this becomes 1/6. Okay, f of x naught means f of 0. Now our x subscript 0, subscript 1, subscript 2, subscript 3, subscript 4 are exactly the same as they were before. That is, x naught is 0, and x of 1 is 1/2, and x sub 2 is 1, and x sub 3 is 1.5, and x sub 4 is 2. So it's f of each of those, and notice the correct coefficients here. The 4, 2, 4, and then 1 coefficients. Okay, f of 0 is 1, f of 1/2 is 1.061, and these you can see from the previous video where we were calculating f of 1/2 and f of 1 and so forth, but there were different coefficients involved in that problem in some cases. So we have, let's see, 2 times 1.414, 4 times 2.092, and then plus 3. Now when the smoke clears on all of this calculation, it turns out that this is 3.24. Now 3.24 is, to 2 decimal places, it is precisely the calculation of the integral of this definite integral that you would get by using the calculator. So to the nearest hundredth, this is exactly like the calculator would get. So that's why I say it's so remarkable as to how accurate this is. And notice that I only carried the calculation of f of these values out to 3 decimal places, when in fact they could have been carried out to other more decimal places if I cared to do that. But certainly if I were doing this by hand 20 years ago, I would only carry that calculation out to several decimal places. And there were charts in the backs of textbooks for square root, so we could actually look those values up. I forget whether the charts went to 3 digits or 4 digits to the right of the decimal, but at any rate we would use whatever accuracy we had there. But that's plenty accurate for this calculation if we're using Simpson's rule. By the way, Simpson's rule was named after a great mathematician. Guess what his name was? You're right, Simpson! Since both the trapezoid rule and Simpson's rule are approximations for definite integrals, it's kind of important if we can calculate a maximum error involved in those 2 calculations. And it turns out that there is a mathematical evaluation of error that can be calculated. The error formula for the trapezoid rule is this. Notice b minus a cubed in this numerator, 12n squared in the denominator. And it's the maximum of the second derivative function over the interval that we're talking about. That is, x, the x that appears in this f double prime of x is between a and b. Could be a or b, but it's in that interval. For Simpson's rule, the error calculation, the error is less than or equal to b minus a to the 5th, 180 n to the 4th in the denominator, and it's the maximum value of the 4th derivative function, and x again appears in the interval. Well, I went ahead and made some calculations here about error for the trapezoid rule right here. Here was the function that we were dealing with before, and we were trying to take this definite integral. Now, the a value is 0, the b value is 2 from here. The n was 4, recall. And if this is our original function, this is f prime of x, and this is f double prime of x. And there are a lot of ways of representing this. There are other ways to show that. But at any rate, here's f double prime of x. Now, I constructed the graph of this, and I found the maximum value along the interval. And this is what I got when I began to calculate the error. The error is less than or equal to, now it's b minus a cubed. The b is 2, the a is 0, and we're cubing here, so we're cubing 2. And then in the denominator, the n is 4, so it's 4 squared. Now, for this part of it, it's 8 over 192. Now that maximum value I found to be 1.468 in that interval. And multiplying here, we find the error, the maximum error, is less than or equal to 0.06117. Now we found the value, I think, to be 4/100ths different from the actual definite integral here. So we're certainly within that range of error for this calculation. Now the Simpson's rule calculation of error is rather interesting. It requires us to find the fourth derivative function, and that was quite an adventure for me. I had to use a calculator. I actually used the TI-92 incidentally for that purpose. But I did find that fourth derivative function, and I found the maximum value along the interval. And here's the calculation that I found for error. It's rather remarkable, and you would expect that the error would be less in using Simpson's rule than using the trapezoid rule, and certainly it turned out that way, even though the n value is the same for both. The b minus a to the fifth, that's 2 minus 0 to the fifth, the 180 n to the fourth. Now n, remember, was 4, so this is 4 to the fourth power. And that the maximum value of the fourth derivative function along that interval is 0.887. And when this all multiplies out, it turns out that the maximum error is 0.000616. Well, no wonder to 3 decimal places we got the actual value that the calculator gets in this calculation. So this is extremely accurate. By the way, I recalculated this on the same function using an n of only 2. Now an n of 2 on that interval, recall, we have a curve, and if n is 2, we have simply 3 points, you see, and so we're approximating that area under the curve by using a quadratic function at the top of that curve and hoping that quadratic function, the graph of the quadratic function, corresponds with the original, the graph of the original function. And it does extremely well. In fact, I found that error to be approximately 1/100th, even, or less than or equal to 1/100th, even if we used an n of just 2.